All right. Hello, everyone, and welcome back to the Geophysics and Tectonics seminar. I'm excited to announce that our speaker this week is Katie Cooper, a professor at the Washington State University, who will be talking to us about Craton stability. What's thickness and shape got to do with it? And so, Dr. Cooper, whenever you're ready, please go ahead.
Great, thank you. And I did want to start off with a big thank you to Keely for organizing this seminar series. I haven't been able to make it all because it often conflicted with my teaching times, but it really did give me a sense of community, even to see those emails come through during a time which often felt a little bit isolating. So I really appreciate it, Keely. And I also wanted to do a thank you too for the tremendous work that you've done to try to remind us that we need to be more inclusive of a community as well too. So again, huge thank you. If y'all want to do like shout out celebrations for Keely, I think that would be great to see too. All right, so to begin also, I wanted to give WSU's Land Acknowledgement. It's a little bit long, but I think it's important to talk about the history that's associated with the lands that we sit on. So WSU acknowledges that its location statewide are on the homelands of Native peoples who've lived in this region from time immemorial. Currently, there are 42 tribes, 35 of which are federally recognized, that share traditional homelands and waterways in what is now Washington State. Some of these are nations and confederacies that represent multiple bands and tribes. The university expresses its deepest respect for and gratitude towards these original and current caretakers of the region. As an academic community, we acknowledge our responsibility to establish and maintain relationships with these tribes and Native peoples in support of their tribal sovereignty and the inclusion of their voices in teaching, research, and programming. WSU established the Office of Tribal Relations and Native American Programs to guide us in our relationship with tribes in service to Native American students and communities. As a land grant institution, we recognize that the Moral Act of 1862 established land grant universities institutions by providing each state with public and federal lands, which are traced back to the disposition of indigenous lands. In 1890, WSU received over 90,000 acres of indigenous lands designated to establish WSU and retains the majority of these lands to this day. We acknowledge the disposition of indigenous lands was often taken by coercive and violent acts and the disregard of treaties. For that, we extend our deepest apologies, and we are deepest gratitude to the Native peoples of this region and maintain our commitment towards reconciliation. And the Pullman location within WSU is located on the ancestral homelands of the Blues people and the ceded lands of the Nimipu or the Nez Perce tribe. Sorry, my computer is now not wanting to advance. We'll give it a moment. It's having a day. We'll just put it that way. And I'm hoping the spinning wheel will eventually stop. No such luck. I'm gonna try to do a stop share right quick and see what's going on. Uh-oh. So I also wanted to acknowledge my colleagues. A lot of this is work that I've done with Rebecca Farrington, Megan Miller, and Louis Moresi as well too. Okay, so if you need to tune out or if I drop off again, let's go ahead and give you the punchline. So it's ever more important to do this in Zoom than in person. So the main point I want to make with my talk today is that lithospheric shapes Cratons literally, but it also shapes their trajectory and connects to some of the most pivotal moments in Earth's history. So on being a Craton, and I think this is important to start with, what is a Craton? What are we talking about? Because I sometimes find myself talking across colleagues when we're talking about what is a Craton with it too. And so I don't know if you came across this article earlier this year, but I accidentally gave a reporter their lead in a story about Cratons, and I called them the secret keepers of the Earth. And if these are the pieces of lands that hold the most geologic history on the Earth's surface currently today, then indeed, this is where we want to point to and try to understand if we want to then understand Earth's evolution from its early days on to present. And so I really do think that they are the secret keepers, and figuring out how to let them tell us our secrets requires to understand them a little bit better as well too. So start off the map of present day Craton locations. I'm sure many of you have seen similar maps to this, but they're often regions that are exposed Archean crust, but they also do then contain other components with them as well too. And when I talk about a craton, what I'm talking about really is the more amalgamation or the craton kind of outline that they're in these kind of types of maps here too. And I think the reason why I do this, and I think it's important to point out, is because then that connects back into what the roots are telling us, or their lithospheres are telling us. And so there are a lot of ways to define a craton, but the kind of classic definition is that it's a region of Earth's crust that has not undergone deformation in long periods of geologic time. And I think that this is a fascinating definition, much like many other definitions within geology, in that it's wonderfully vague. And it doesn't necessarily mean what type of deformation, how long of geologic period of time, which is interesting because it gives us wiggle room, but it does point out to kind of the key point is that it's something that hasn't done much for a long period of time. And the more modern deformation includes then the lithosphere and adds it to this, which then starts building up my point of, again, the lithosphere is really what's then shaping this long-term trajectory of these regions of the Earth. And so this reason to point back to the lithosphere is if we start looking at some of the first order observations of cratons. And so these are images from two different clustering observation or driven studies. And the first one is looking at the surface down through the crust. And what these authors did is that they then took seismic and other geophysical measurements of the Earth and started doing a clustering analysis to see which things are like or similar to other regions. And you'll notice that they did their clustering method over here, and they started giving it some terms to it of oceanic, Archean. So connecting back into surface observables of these regions as well. And you can see that there some things start popping out, is that you see origins being similar to each other, Archean and Proterozoic regions being similar to each other. And this is again looking from like surface down to the crust. Now, this group here, instead, they looked at the entire lithosphere and did a similar clustering analysis as well. They didn't prescribe necessarily names to it, but again, looking at what regions are like and similar to each other. And you'll notice it has very similar kind of clustering, and we chose to do a coloring scheme also to point out those similarities within it too. But in these kind of bluey bands regions, we see then, if you remember back that map of where cratons are, that there are some interesting similarities that a broad brush global feature between these different regions on Earth, and they seem likely probably connected back to the lithosphere. So another observation to think about too is then if you're plotting up the relative crust versus the lithosphere on it. So then 1 means that they're almost equal, or they're equal, I should say. 0, then you're looking at the lithosphere dominating this ratio of thickness. And then if you do this kind of map, then the cratons really do start popping out and looking very similar to each other. And what's interesting, if you do the same kind of looking at it, if you just look at the crustal thickness, you do not see necessarily any similarities between cratons if you're just looking at crustal thickness. But the similarities are starting to pop out when you start including the lithosphere with it too. And indeed, this is kind of one of the key early first observations about cratons, is they are associated with the thickest lithosphere on the Earth. And so plotted on this map here is depth to the lithosphere asthenosphere boundary, where the thickest regions are then colored in the darkest blues, and middle 130 to 250 kilometers in this light blue here too. And then we left everything else to be a little bit lighter, so just so that way we can have these things pop. And indeed, where we see the thickest lithosphere on the Earth is the Cratons. And then if we look at something other than geophysical techniques, and we look at the samplings that are provided through kimberlite eruptions, and we look at the xenoliths of the Cratons, indeed it seems like they're associated with very thick, somewhat cooler, pretty chemically distinct lithosphere with it. And another first order observation to make about these is just like that kind of vague definition of Cratons, these regions have pretty old ages. And so samples from those like roots or the keels or the bottom lithosphere of the Craton span a significant old age for their formation. Yet we almost, when we start talking about stabilities of Craton, we almost argue that they're stable despite their roots. And this is because, again, those first order observations are pointing out that they're old. They're also cold. If you look at the surface heat flux, these are also associated with the lowest surface heat flux on the Earth. So we would expect them to be dense and want to sink into the mantle and not remain stable or exist for a long period of time. So even though we argue that they're stable despite all of their first observations, they're actually supplying the stability themselves. And so the early idea for this is that, again, if they're old, cold, and dense, the reason why they're sticking around is they're essentially neutrally buoyant. So that thermal, negative thermal buoyancy is being exactly offset by the positive chemical buoyancy. And so this is this idea of isopycnicity. And so when we then go and look at all the Cratons, though, and we then plot them out and we make predictions about how their densities or the magnesium numbers should change with depth, they don't really actually, they aren't perfectly isopycnic at every single level. On the integrated kind of thick lithosphere thickness, they do tend to work out a bit better. Some of them do follow the isopycnic line a little bit better than others. Some of them do not follow this at all either. So there's a lot of ideas for then what is supplying the Craton stability. That buoyancy idea of, again, if they have some sort of positive chemical buoyancy, they can then offset that downpull that would be associated with being old and cold. However, that doesn't do it all alone. If you want to get into that conversation, we can during the chat. We also then talk about its rheology. So they are cold, so then they would be viscously stronger. We have reasons to believe that they would also be drier, which that would also then make them stronger as well. They could have higher yield strength. They could be surrounding by weaker materials, which then those weaker materials then deform as opposed to the Craton itself. But I'd like to make that argument really that all of these different things are really just connected to the thickness of the lithosphere itself as well. And so to make that argument, I'm going to turn to stability regimes. But before we get there, just to get again on the same page about how to interpret stability regimes, I just wanted to give a little bit of how to interpret and read these diagrams with it. So below here, I've plotted up some property A against some property B. And I have a line here, and this line demarcates the transition between behavior 1, which happens for the values of property A and property B, which are in this space, versus behavior 2, which then occurs for then parameters within property B and property A within that space. So above this line, we predict behavior A to happen. Below this line, behavior 2 happens. So then let's turn back to this idea of that Cratons are stable because they have an enhanced buoyancy associated with them. So if they have an enhanced buoyancy associated with them, we should be able to then come up with a relationship of how much more buoyant they need to be than a thermal downwelling that would be associated with it. And so for this, we plotted up here a scaling relationship that says just that. This is the buoyancy ratio, which is talking about the density differences between the cratonic lithosphere and what it's sitting in just surrounding average mantle. And that buoyancy ratio then also then depends on the temperature difference between the two bodies as well as then the thermal expansion. So again, this would make sense if something is cold, it would contract and then want to sink down. So this is what we're looking at with the buoyancy ratio between there. So in order for this to be stable and resist kind of that being entrained within the thermal downwelling, it needs to be larger than the mantle Rayleigh number. the mantle Rayleigh number is a non-dimensional number that's representative of the convective vigor of the system. So the higher the Rayleigh number, the more vigorous the convection. The lower the Rayleigh number, the less vigorous the convection. And so this also then scales with the size of downwellings as well as many other things as well too. So what this relationship is saying is then that the buoyancy times the thickness of the lithosphere or the integrated buoyancy of that entire lithospheric package has to be then larger than the Rayleigh number. All right, so down here, I've plotted out what the stability regime would look like for that relationship. So I've got the Rayleigh number on the bottom here. We have higher Rayleigh numbers on this end. So another thing to think about with the Rayleigh number, it was likely higher in the past because the mantle temperatures were higher. And then as the Earth is cooling, the Rayleigh number then decreases. So you can also think about this bottom axis as also kind of a proxy for time to keep in your mind. And this is then plotted up against the lithospheric thickness over here. And then this line here is the relationship that I have written out there. So above this line, we predict stable behavior, so no deformation of the craton. Below this line, we expect some sort of deformation, whether it's dripping or full scale recycling into the mantle itself. So we can do this for multiple different chemical compositions of the cratonic lithosphere. And so before I was just showing out one buoyancy ratio, now I'm showing multiple ones here. And as we're then decreasing the buoyancy ratio, we're decreasing the chemical difference between the Craton lithosphere and then what is sitting within the mantle. So it's becoming closer and closer to the mantle composition. So the first thing to think about and point out is you'll notice that this curve curves as it is. And so, and what I think is interesting to think about is if you have different compositions here, you then reach stability for different thicknesses at different compositions. So if we're at a single Rayleigh number, so around 10 to the 8th here, depending on your chemical composition of the cratonic lithosphere, either the craton is going to be stable at pretty shallow thicknesses, around 50 kilometers, or if it's, again, less chemically different than the mantle, it needs to be much thicker to be stable. Now, I think it's important to talk about, and this is like one of my many soapboxes, is when we're talking about stability, that's not necessarily the same thing as longevity. Stability means that you can resist deformation in a current dynamic setting. So like one Rayleigh number. But longevity means that you need to resist deformation over a range of dynamic settings as then the Earth is cooling. Those dynamic settings are also going to change as well too. And so this is where I think these regime diagrams become really important, because then we can start talking about longevity too. So longevity, rather than just thinking the point at which stability is achieved, rather now think, what is the range of Rayleigh numbers over which the craton will be and remain stable? And so if you think about this, so again, this curve curves, which is convenient. If you look at near the thick lithosphere, thickest regions of the lithosphere here too, no matter the composition, the thicker the lithosphere is, the longer the range of, or the larger the range of Rayleigh numbers over which it'll be stable. So the longer it will remain stable as well too. Again, if we think about the Rayleigh number as being somewhat proxy for geologic time, higher Rayleigh numbers in the past, lower Rayleigh numbers in the moving towards present, that then again tells you as the Earth's cooling, you can then remain stable for a longer period of time. Again, this is still compositionally dependent, so the more buoyant the material is, the longer you can remain stable as well too. Now, if you have thinner lithosphere starting off, you have shorter time periods over which you could be stable, or smaller range of Rayleigh numbers that you can remain stable. So thicker lithosphere promotes longevity. And we're having issues again. There we go. Okay, so now let's turn to another different driver of stability for Cratons. It's yield strength. So will it deform in a localized plastic manner or not? So we can build up another scaling relationship for this, where now this time we're comparing the friction coefficient of the material times its the thickness of the lithosphere, so it's integrated yield strength. And it too needs to exceed the Rayleigh number to the -3rd value. And so another thing the Rayleigh number scales with is convective stresses with it too. And so this is where this is tying in. So in order for it to resist deformation by yielding or shearing, then the yield strength of the material must not be exceeded by the convective stresses. So down here, plotting the Rayleigh number on the bottom, just like before, lithospheric thickness, this is the relationship on the right here for a single friction coefficient value. Everything above this shouldn't experience yielding behavior. Everything below this will then experience some shearing. All right, so just like within the buoyancy, stability is also then dependent on different friction coefficient values. So then this can connect back to whether you have a lot of really weak faults or you then have poor fluids. Those are things that then could change the friction coefficient values. So just like before, you can achieve stability at different thicknesses depending on these values as well. And also, just like before, thicker lithosphere also promotes longevity. Again, this is independent of friction coefficient value, but the higher the friction coefficient value, then the longer period that you can have for a craton within itself. If it starts off thinner, that is a smaller range of Rayleigh numbers over which it remains stable. So then I start thinking about what are the implications of longevity for Craton? If they really are, again, long-lived features, this is likely them pointing to that they've had pretty near constant lithosphere thickness for their duration, because again, that's what's helping provide longevity, as we saw from those stability regimes. So then what does this mean for the life history of a craton if it's just moving around being wonderfully thick? And so this can then play some interesting first order roles on larger geologic history. So let's orient ourselves for this very interesting picture, which I like to call kind of, oh, sound like somebody was having fun. All right, so I like to call this the croissant. And then this, but what this is that we've now taken the continents and moved them back into their Pangean configuration. And we took the seismic imaging of the lithospheric thickness. I say we, it wasn't me, but took the lithospheric, the seismic imaging of the lithospheric thickness, and then took that and rotated it back to the configuration of the continents during Pangea. And so it's hard a little bit to see the outlines of the continents on here. This is South America here. There's Africa there, if that helps you. There's Australia there to orient it. And here's your map kind of guide to look at it. Yeah, it helps to me to turn my head to look at it as well too. What was cool about doing this, which I was like, how creative, how wonderfully creative to do this. But what's cool about this is you can see where the cratons are coming out here, but between the cratons, you have this curvy linear trend of all of the thick lithosphere. Which then the authors suggested that this is likely due to them acting almost as resistors or bumper cars during this assembly, which then thickened the lithosphere between it. And so these regions that are still thick, that are not necessarily craton, are left over from this last continental assembly, supercontinental assembly. Another cool idea that, again, very creative, is that having something that's very thick and long-lived also has control over when continents emerged out of the oceans as well too. And this is something that Cinti Lee and his group presented, and when I heard it, I was like, oh my gosh, this is so cool. All right, so the idea here is, this is plotting of age against elevation. So This is sea level, elevation 0 here. And these are different lines representing different models of when you would expect then continents to become submerged out of the oceans or emerged out of the oceans with time due to buoyancy differences. And so if you look at this kind of range here, which this is, each one of these are for different continental crust thicknesses. And so this is kind of our average continental present day crust thickness of 35 to 40. And if you follow either the red bands or the blue bands in the past, when we expect the continents to then emerge out of the oceans is probably within a billion or so years ago. And the reason why they came up with this idea is then it starts thinking about what are the controls on what would then, when you would then start having continents rise up out of the mountain, out of the mantle. So remember, the mantle was hotter in the past. And so then we have these things that are neutrally buoyant. They may not have always been neutrally buoyant due to, again, this depends on their relationship to the mantle that they're sitting in. And so then if you start thinking about the structure of Cratons, the way to think about it truly is that embedded transitions within there. And that we often talk about Craton lithosphere, but it becomes important what we're actually meaning by it too. So Cratons, because they're long-lived and they seem to have this unique kind of chemistry to them, they are also a chemical boundary layer within here. And so there's chemically distinct material that contains the crust and the root within here. That's then sitting within a thermal boundary layer. And since this is thick and it does not deform, since the Craton is long-lived, then it's not going to make up the entire thermal boundary layer. It's going to make up a good portion of the thermal boundary layer, but that is going to then cause all of this area here to only conduct heat. And so then it's taking up a large portion of the thermal boundary layer, but you still then have a region around it, which somebody once coined as the thermal aura of a Craton. But this is the region that it's cooling, or surrounding it, that then sits into the mantle. Now this kind of like behavior here then puts a long-term control on the thermal structure of the Craton itself. And so this is the very first paper, and I did not know it was going to be used in this way, which is really fun. But where we then plotted out and determined the relationship between the thermal to chemical boundary layer thickness within there. So we set the actual chemical boundary layer thickness. This is plotting up down here, either to have no root, this is 40 kilometers, to then having 200 kilometers, which is a 40 kilometer crust with 160 kilometer chemically distinct root on it, and then mapped out the corresponding thermal lithosphere that's associated with this. So what was the region into the mantle that then it cooled surrounding it, plus then its chemical distinct material. And what we found is that as you increase your Craton lithosphere thickness, the ratio between the two values started planing out and becoming closer, meaning that that chemical or that convective sublayer beneath the chemically distinct region started to thin out, and it became closer and closer to each other. Again, showing and indicating that it's having the largest control on the thermal structure, no matter what the mantle is doing. So because of this, this is acting as an anchor for your overall continents. And so then as in the mantle is cooling, you're still having the Craton acting as an anchor. And once then the mantle cools sufficiently to the point, it is only then that that anchor will allow the continents to move up enough to then emerge out of the oceans. Now they also pointed out to this could have happened right around the transition into the Cambrian, and having the continents then moving out and be more exposed to then the surface and weathering, that could have flushed a lot of nutrients into the oceans, and boom, Cambrian explosion. And when you realize that your very first paper might actually connect to the origin of trilobites, you know you've made it as a scientist, I think. I don't know, we'll see. It's a cool, again, another really fun creative idea. So again, before I transition to the next part of this, just want to point out that really having thick Cratons, or their thickness, is a first order characteristic, as well as then a primary control on their stability and their longevity. And then this impacts what happens to continents as the continents move through time. So then I'm like, okay, thickness is really important. Why are we drawing this shape for Cratons? I don't know if if anybody else does this, but when I draw a Craton, this is automatically the first thing that I draw. But the more that we look at how Cratons look in seismic imaging, the more variety that we see. And we see a lot of really interesting shapes to Cratons. And sometimes we do see this gradual thickening, so that kind of trapezoidal looking shape. Sometimes we see very dramatic and abrupt transitions to Craton thickness, like here for Western Canada, where we see almost a vertical kind of margin to the Craton too. Sometimes we see stepped increases like we see in Eastern Australia, where if we look at this interpretation here, it's like stair stepping into the thickest region of the Craton itself. Another region where we see a stepped increase is the northern part of South America, where there seems to also, again, be moving from like this is thinner lithosphere to thicker lithosphere, so there is a bit of a step there. And I'll just point out this is really interesting because where we see the stepped is also where we see a subduction zone almost orthogonal to this Craton margin itself, which is kind of interesting itself, and we'll come back to that. And we also know from geodynamic simulations from Curie and Van Wyck that Craton margin shape can evolve with simulations. And these are two different examples. Here, the other Craton is a bit weaker versus the one on the right where it's strong. They both start off with the same shape, but one remains consistent as you move through geologic time, and the other one then starts pancaking and flattening out, and then you have a different transition associated with it too. So you can either preserve or modify a Craton shape depending on its rheology. So then this like brought up some ideas, and we're like, well, this is interesting. Like, first of all, what is it about Craton shapes? And like, by having these interesting shapes, are they helping drive mantle flow? And then also, could that mantle flow then potentially lead to their demise by this? And this was inspired by one of those interesting tectonic settings that I pointed out. If we have, again, the northern portion of South America here, where we have this stepped increase onto the Amazonian Craton, and we have this interesting subducting slab abutting against it. The slab is rolling back and driving mantle flow right along this margin. And so we were wondering, is the reason why it's flowing here because of the shape of the Craton? And does this actually start to enhance the flow, which then that could potentially lead to further erosion of the Craton itself? And then we were also then looking over at the West African Craton, where we have a similar-esque tectonic setting. And again, a lot of mantle flow moving up along that margin as well. So we decided to set up an experiment to see what are the kind of connections between mantle flow and Craton shape, and what does that tell us about Craton stability? So this is just the geometry of these settings to get us all oriented before we start showing the images of it. So what we did is we put South America into a convecting box with here, and then we gave it different margin edges. So we put this into just an average mantle, an average oceanic lithosphere, looking at bird's eye view here, down to there, and put a slab butting up against the Craton itself. This is then now looking at a side view. North is over here. So this is our Craton, again, sitting in just averaged mantle. And we see here we have different shapes. We have then a tiered shape, stepped increase here. We looked at a gradual increase, so that kind of traditional trapezoidal shape. Then we also looked at a vertical or dramatic kind of margin, and we had a vertical margin right against the slab. And then we also then had a vertical margin further away from the slab, introducing kind of a channel within the region. And then we put our slab in here as well. All right. So once we set all of this up, we then started doing a series of instantaneous flow models. And we used Underworld 2 for this, and made these pretty highly resolved as well too. So down here, this is showing the initial thermal structure of the simulations. So north is up here, so we're looking this way into it. So here's our slab dipping into the mantle here. This is the Craton. You can see the outline of the tiered shape into the thickest region. And then these are just different, again, initial temperature conditions that we set to it. And so we initialized the temperature field using half space cooling models, and we prescribed Craton thickness, oceanic plate age, subductive plate age, and then put a free slip boundary condition on all of the walls. We then used a temperature and strain rate dependent dislocation and diffusion rheology for it. All right, so first to orient ourselves, let's look at what we would expect the flow field to be just for the Craton itself. And so the same kind of orientation as before, we're looking at into the Craton here. There's no slab here, this is Craton only. You still see the outline of the tiered shape along there. This is what we coined as devil's eye view, where imagine you're at the bottom of the simulation looking up underneath the Craton. Again, we wanted to look at those transitional shapes, and we thought that this was the best way to peer underneath the Craton to see what was happening along the margin. So what I've plotted on here are the velocity vectors. And these are scaled up to 10 times. And you'll say, these are really tiny. And indeed, the flow field associated with just having the Craton in there is very, very small. And if I didn't scale these up, you might say, Katie, there's nothing there. Maybe your computer is messed up again. That's not the case. Otherwise, you just wouldn't see them because they're just that small. So in comparison, let's look at the slab only flow field. So this is similar orientation as before. We have our slab moving in here, and we see that the slab is then falling back and then driving large toroidal motion. And then if we look at, again, from the devil's eye view, we get another perspective of that toroidal motion as well too. And these velocity vectors are not scaled up with it too. So this is then the larger control of all of the flow fields, which is what we want. Awesome, we set this up correctly. All right, so now combined flow fields. So this is the slab here, the Cratons here, we have our velocity vectors. And then again, this is looking at it from below the devil's eye view. And what we're seeing is that this large toroidal flow field is being channelized along the Craton margin itself. So indeed, having that slab there is driving motion right along that slab. And that all the small scale convection that was happening just to having a Craton there is completely swept into that larger mantle flow field. So let's now compare this for different Craton margin shapes. So we have then the more transitional diagonal here. This is then having a vertical margin that then is right up against the Craton or right up against the slab, though there is space in between there to let the material move through there. It's a much smaller margin, as opposed to then right here where we then move that straight vertical margin further away from the slab within it too. And we can see that this channelizing behavior is happening for all of the different shapes, with the least amount happening for when we have the smallest opening for the material to move through there, which makes sense with it too. So we do see that there is some sort of interaction happening between the Craton and the subducting slab itself. But what are the consequences of having essentially channelized flow right along those margins? And how does that depend? So for that, we wanted to turn and look at something different. And so we're going to look at the strain rate, which then tells us about the potential for material to deform. And so to do this, we then took some sampling transects. So now we're looking straight south into the models here. We have our subducting slab. This is for the tiered margin Craton itself. And what this blue line here is, I have to like remind my brain to do this correctly. This is going in and out of the screen. And this is a sampling transect. So everywhere along there, we take a measurement of the strain rate. So this is taking it in front of the slab, moving into that channel in between the slab and the Craton, and then into the Craton itself. All right. So this is then the plot of these strain rate profiles. And so before we start looking at below, let's go ahead and orient ourselves on how to like interpret and read these this very busy graph. All right, so this is distance along the transect. along the bottom, and we're plotting this against the log of the strain rate. So up at top, again, we're moving south into the model itself. Up at the top, we have here the solid gray line, that is the sampling transect. And what we then put on here to help orient ourselves as we're interpreting this is then the location of the lithosphere or the Craton margin. So if we follow this red line here, this is then the shape for the tiered, oh no, that's not, don't listen to me. This red line here is then for the straight margin that then is furthest away from the slab. The blue line here is for the tiered shape margin. The green line is then showing the location for the straight vertical margin that's right up against the slab. And then the orange is then for the diagonal shape. So along this transect, the transect intersects and moves into the interior of the Craton at this point Y for the straight, this green line, the straight proximal. It moves into the Craton for the diagonal at X, as well as then for the straight distal, so the further one away at X. And then it runs along the transect for the tiered and doesn't enter into the Craton until this point within it too. All right, so now let's look down below. So just as kind of comparison, this dashed line in black is then for the slab only models. These dashed line here are for the Craton only models. So you can see strain rate dramatically increases once you put a falling back slab into the system, which is what you would expect. All right, so these straight lines here are, these solid lines here are for those that have the Craton and the slab interacting together. And so as we're then moving in front of the mantle, moving along here, we see some interesting increased strain rates again, which is what we expect. But things start getting interesting as we start moving towards and moving within the Craton, is that we see the channelizing of flow and ramping up strain rates right along the Craton margin. But different behavior happens for the different shapes of the Cratons. For those that have like the vertical Craton where you go immediately into a thick Craton, the strain rate is dampened down dramatically as you move in there. Now, if you look at the orange and the blue, which show progressive thickening, either through a gradual diagonal shape or through a tiered shape, those increased strain rates move into the Craton material itself, meaning that you're then making those regions more likely to deform. And so again, just to follow along the orange line here, as we're entering into the Craton, we're in the Craton region here, we still have increased strain rates within the Craton itself. The same way for the tiered shape too. Meaning that what this is indicating is those straight vertical margins are the most stable of shapes. And that for these progressive thickening margins, those are the most susceptible to deformation. And you could end up in the case where they start eroding away until they reach a more stable kind of configuration. So then we're like, well, that's interesting, because these two cases that we thought were really interesting show an interesting progressive thickening. So within the South America and Amazonia Craton here, we have this tiered shape. And we see these are, I forgot to mention this, the other plots, my apologies. These are observations of anisotropy and splitting. And we see the highest splitting happening within this margin, and that these are moving into the Craton regions, but they start dampening out just like we saw within our simulations. Same way for the West African Craton, which has a more gradual increase to the thickness. We again see larger splitting rates within within the channel, and those then extend and move into the Craton itself, eventually dampening out when you get to the thickest region. And so are we catching some sort of progressive erosion happening within the Cratonic lithosphere, and are they changing shapes? And do these anisotropy patterns then reflect that inward progression of deformation happening within the Craton itself? So to start wrapping this up, both Craton stability and longevity are linked to Craton thickness. Their shape, or if you just want to think about it, all shape is just variations in lithospheric thickness, also contributes to the stability, with some shapes promoting stability over others. And this dependence on shape could then potentially lead to runaway processes where you have continual and perpetual Craton erosion until a more stable shape has been achieved. But nothing's ever really truly concluded. So things that I'm still kind of curious about is, again, what are really the consequences of having long-lived, thick thermal boundary layers? Because that's short-circuiting some of the scaling relationships we know about how a planet evolves. So does this change the thermal evolution of a planet? Is this keeping continents around on the Earth, or is it limiting further continental growth? And then on what timescales do Craton margins evolve or remain stable? What's the interplay between rheology and shape? And then what are the consequences of progressive erosion, and how can this be captured within the rock record? And these two questions are something that I'm then working to explore further with some colleagues and hoping to submit a proposal on it soon. So to leave you with where I began, lithospheric thickness shapes Cratons literally, but it also shapes their trajectory and connects to some of the most pivotal moments in Earth's history. And so apologies to Tina Turner, what thickness got to do with it? A lot more than a second-hand emotion. So thank you all.
Thank you. I'll applaud for everyone. You get your virtual applause. Very cool stuff. Thank you very much. Do we have any questions? I saw some pop up in the chat. Paul Mueller, would you like to ask your question?
Yeah, what struck me was, do these channels of flow along the margins of a craton capable of, is there enough strength? That's not right. Basically, can this flow start shearing the Craton margin to the point that this could be a potential way to generate ribbon continents, as opposed to subduction and back arc spreading and so forth, that eventually separates out terrain from a Craton? And what I'm thinking about is the Appalachians, where we have a long sequence of Gondwanan and peri-Gondwanan terrains, ultimately accreting to the margin. The question is, under what environments were these terrains separated from their original Cratonic parent?
Ooh, that is fun. And that's what we're hoping to get at, to do the 3D fully dynamic simulations to see if we can see some of that type of behavior. We can see again in 2D that you can have some interesting deformation along the margins, but to see kind of parallel flow, you've got to do the full 3D. And so stay tuned for that. Those are a bit gnarly of simulations to do, but I'm excited for the challenge.
So that's Cooper et al. 2022?
Yeah, we'll go with that. Probably 2023. Let's be more realistic.
Thank you.
Okay, thanks.
Thank you, Paul. Matria Deepa Baruha had a question in the chat, which was any update of the strain rate for the Darwar Craton in India?
We haven't looked there, but that's a great idea. Thank you for that.
And Maureen Long, I see you have your hand raised.
Yeah, thanks. Thanks for an awesome talk, Katie. Good to see you. I absolutely love, you will be unsurprised to hear, the idea of subduction-induced mantle flow playing a role in shaping the edges of these Cratons. I absolutely love it. It's a super cool model. And my question, I mean, kind of touching on one of the points you made on your very last slide, thinking about, can we look at the geologic record for evidence that this has happened in the past? And I guess I wonder whether our plate, I know plate tectonic reconstructions, of course, they're not great as you go very far back in time, but can we look to plate tectonic reconstructions and look for other examples where we think there may have been subduction-induced mantle flow next to a Craton, and then look for evidence that the Craton margin there has assumed this stable shape that might be predicted by the models. Are there any prospects for that?
Maybe. I think the first step is when like, this is what we're thinking is like, where in the geologic record can we look for potentially signals for the margins evolving? And so I'll do a plug for Emily Chen's work, is that she's looking at changes in zenith texture to look at different deformation kind of events happening. And so that's one way I think of looking. The other one that we're curious about, or wondering how it may pan out, is like, are there any evidence within erosion rates or what is the word I'm looking for? Moving sediment cover. That's what I'm looking for too. It's like, if you imagine that if you have some evolution of the margin, you may expect some up and down behavior associated with that. But that's going to be hard because like, you're also capturing a lot of different other things within the sediment record too. So I don't know. First step first is figure out that. And then that might give us a bit of more of a chance to say, okay, can we then find evidence for these shaping events?
Excellent, thanks.
Thank you. Other questions for Dr. Cooper? John Arthur, did you have a question?
Hi.
Yeah, I was thinking of something. You showed the West African Craton against the European Craton, and at the Gibraltar Straits, there are a lot of red lines. Now you talk these being splitting, but that's at some depth, isn't it? Unless it's actually translating that into the upper part of the geologic section. So how deep are those splittings?
I don't remember at the top of my head, and I think this is in general, the big challenge is like, where along the path is that behavior happening? But I think that there's reasons to believe that that is happening within upper mantle and above. So I mean, that is kind of the question. And that's also the nice thing we could do as well too, is then take another kind of sampling transect with our models to say, where would you expect to have higher versus lower strain rates? And so that's another way of kind of like getting at that information too.
And what sort of depth is that?
I'm sorry, what?
What sort of depth is that below surface?
Oh, below the surface. I don't think that they're saying that that is then frozen in anisotropy, and so you're really looking at the flowing mantle in that case.
Okay, thank you.
Thank you. John Yuan, would you like to ask your question now? Thank you.
Hi, Dr. Cooper. It's a great talk, and I really enjoy it. So I have a question for also for the Rayleigh number and the thickness, lithosphere thickness plot. So there is a straight boundary between the stable and the deformation domain. So I'm wondering if there is transition boundary, it's kind of metastable or kind of between them. Is that very clear?
Yeah, so what I didn't plot out on there is that we tested those scaling relationships against models themselves with it too. And like, I'm guessing that likely so, that they're probably, you could draw that line a little bit thicker, because when you then look at, to test that out, I did like thousands of simulations within there too, but like sometimes that behavior is not clear cut. And I think that's an important thing whenever you look at any kind of regime diagram, likely those are fuzzy boundaries rather than extreme boundaries. And that some of it is like interpretation, but some of it is like truly like you capture some transitional behavior. So really great point. Okay, and then how do you define stability? It's kind of how long you can say it's stable. It's 100 million. So yeah, within those simulations, several mantle overturns. So you're looking at like several hundreds of millions of years where nothing is happening, and it's truly a very boring simulation. Okay, and then I have that last question. So for the cartoon you draw, I really like it, and it seems like it's a widely accepted cartoon for the lithosphere and the crust. So the shape, I'm wondering why I know according to seismology, the lithosphere below is very thick, okay. So I'm wondering why it's so thick compared to the crust, because the
the lithosphere below the craton is kind of depleted after the craton formation. So after you get some depleted, you form some crust, but the volume seems very big contrast. You don't need so much depleted lithosphere to form that craton. I don't know what's the relationship between the volume and how that
Right,
comes
and
from.
like that's going back to like how do you even form these like really thick, strange things as well too. And like yeah, there's a bit of like a volume game that you can play. And so like another thing to look at is you have those magnesium numbers for the xenolith themselves. And what they're indicating is that there was a large amount of melt extraction. But even then, you don't necessarily have that crust left over anymore. And so one of the ideas is instead of having just make the crust and then you're left with the residue, then instead you made like thinner regions and then you thicken them together. And that's likely what's driving that idea for that trapezoidal kind of traditional shape, is that thickening process, you would have the thickest regions in the middle and the thinner on the outside with it too. So it's not just a single shot likely to then make that, unless then, I mean, it really is likely you're going to have to then have the melt extraction process and then do the thickening to end up with that, having that volumetric as a difference.
Okay, that helps a lot. Thank you.
Thank you. Ling Chen had a question in the chat about the kind of lithospheric thickness in the thickness versus Rayleigh number plots that you were referring to. So if you consider different properties, then you have different measurements of lithospheric thickness. So I guess, yeah.
Correct. And so what's plotted out in there is that chemically distinct lithosphere as opposed to then the thermal lithosphere for it. Gotcha.
Okay. Thank you. And Paul Mueller, you had a follow-up question.
Yeah, rather curious about the subconvective boundary layer, basically surrounding the craton. What composition do you assign to that? Could that possibly reflect melt paths around the craton?
Maybe, but really,
flow?
yeah. I'm a little agnostic about like what composition those could be, because like those are really then driven just by the cooling craton sitting within the mantle itself. So whatever is around it then gets cooled, but that potentially could be there. But again, it's not as important to me as like, I mean, not that I'm saying that it's dismissive, but I'm saying that's not critical to know about the composition because the cooling is going to happen regardless. If that makes any sense.
Well, I'm just wondering about it being a possible flow conduit.
Maybe.
Since you're isolating it from the convective part of the mantle, can it have its own flow?
Maybe, and that is another question too, is like, are they sticking around with the craton and how long? There are seeds for drips within the simulations, so you could have drips coming off of it. And that could be an idea. Drips comes off of it, you thin that layer, and then it cools back through it. So it could either be pretty static or pretty dynamic, but that may depend on a lot of things that still need to be explored.
It just seems like those are, if they last long enough, are potential loci of the events that ultimately disaggregate the craton or cratons. If they're now surrounded by these things, did those have a role in separating the craton from whoever its partner was?
Maybe. I mean, that's another thing too. You could think of them as another kind of like buffer region, is it could be taking up the deformation as opposed to the craton itself, since it's slightly weaker than the craton. And so then if you have it slammed together, that could be the region that may be deforming as opposed to the chemically distinct one. So maybe. Okay. I don't think they themselves would drive split up though.
Okay. So,
and the reason why is to look at those craton only flow fields, only small scale convection, which is likely coming from that convective sublayer, is happening, as opposed to that big flow field being driven by things like slabs.
Right. Okay, thanks.
I see questions about the mantle plume can heal the thinned craton within it too. I have to spend more time thinking about this paper. I've read it a couple times over and I just haven't had like the nice quiet time to really like think about it too. But it's a very intriguing idea, I would say.
Are there any other questions for Dr. Cooper? Well, I guess I'll ask one. I don't study Cratons. I was curious if the like horizontal extent of the Craton made any difference, or just the thickness, with things like both shape and stability for boundaries, and yeah.
Yeah, I'm curious about that one as well too. Is there a reason why we see them collectively together? And I'm kind of wondering if that does play a role too.
Okay. Add it to your list of questions you're still curious about.
I know.
Thank you. All right. Are there any last questions for Dr. Cooper? If not, then let's thank Dr. Katie Cooper for the wonderful talk and great discussion.
Thank y'all. I really appreciate it.
Thank you very much. And you're welcome to stick around and chat with each other if you would like.